heard of a device that is used to reduce or increase the voltage of an alternating current? It is called a transformer. It works on the principle of Faraday's law. Faraday has given many different laws in magnetism. Let us learn about his laws in detail with this video. We already know that due to the relative motion between a magnet and a coil, the current is induced in the coil as indicated by the galvanometer. To know more about this phenomenon, we will study Faraday's laws of electromagnetic induction. Faraday's first law states, whenever the amount of magnetic flux linked with a coil changes, an EMF is induced in it. This induced EMF lasts as long as the change in the magnetic flux continues. Let's understand it in detail. We can see that when the magnet is at position X, the flux linked with the coil is 3 Weber. On moving the magnet to position Y towards the coil, the flux changes to 9 Weber. That is, magnetic flux linked with the coil has increased. We also see that during the motion of the bar magnet from position X to Y, an EMF is induced as indicated by the galvanometer. When the magnet is stationary, the EMF is 0 and the galvanometer shows 0 deflection. Similarly, if we move the bar magnet away from the coil, the flux again changes from 9 Weber to 3 Weber, and so again an EMF is induced. But this is in the reverse direction as shown by the galvanometer. Once again, when the magnet is in a stationary position, the galvanometer shows 0 deflection. Faraday's second law. The magnitude of the EMF induced in a coil is directly proportional to the rate of change of magnetic flux linked with it. We can understand this law in a better manner with the help of the following 2 cases. Case 1. Initially, we see that the flux linked with the coil is, say, 3 Weber. Now, within a time interval of, say, 10 seconds, we move the magnet closer to the coil such that the flux linked is 5 Weber. So we can say that in these 10 seconds, the change in the flux is from 3 Weber to 5 Weber, that is 2 Weber, and the induced EMF is 0.2 volts. This corresponds to a deflection of 5 divisions in the galvanometer. Case 2. Again, we take the magnet to the initial position such that the flux linked is 3 Weber. But now, in 10 seconds, we move the magnet towards the coil such that the flux linked is 7 Weber. Thus, in these 10 seconds, the change in the flux is from 3 Weber to 7 Weber, and that is 4 Weber. And the induced EMF is 0.4 volts. This corresponds to a deflection of 10 divisions in the galvanometer. Generalizing the above 2 cases, we can say that if phi1 is the magnetic flux linked with the coil initially, and phi2 is the magnetic flux linked with the coil after time t, then the rate of change of magnetic flux is equal to phi2 minus phi1 over t. By Faraday's second law, the induced EMF E is proportional to phi2 minus phi1 over t. Let d phi equals to the change in magnetic flux in time dt. Therefore, E is proportional to d phi over dt. Let's have a quick recap of what we've learned so far. Faraday's first law. Whenever the amount of magnetic flux linked with a coil changes, an EMF is induced in it. This induced EMF lasts as long as the change in the magnetic flux continues. Faraday's second law. The magnitude of the EMF induced in a coil is directly proportional to the rate of change of magnetic flux linked with it. Mathematically, E is directly proportional to d phi by dt. Now that you've learned about Faraday's law, let me tell you that based on Faraday's law, there are many discoveries, such as musical instruments like an electric guitar, electric violin, that have taken place. Try listing some more applications until we meet again.